Talk of the conference, and I really thank you for now, after everything we've learned about time, to be willing to learn a little bit about quantum gravity. So the title of my talk is that baby universes need parental watch. Usually babies get stuffed animals when they're born, but apparently universes get Philippe Patek or Cartier watches that synchronize to that of their parent upon their arrival. And that's the thesis that I want to convince you of. So this is a very physics-heavy talk, and I'm going to do my best to digest it and simplify it so that it's accessible. But of course, if you have any questions for clarification, feel free to interrupt, and then substantive questions we can leave till the end. And I would appreciate actually a 25-minute heads up if that's all right. Okay, so I just want to acknowledge that this is joint work with Baptiste, also here at the University of Geneva. And this is the game plan for today. I'm going to talk about a paradox that fulfills the contradiction component of the theme of the workshop, and it's the infamous black hole information paradox. I'm aware that many of you probably have not come across this before, so I'm going to give you a breezy tour of what's going on, as well as my interpretation of why the paradox is important. And then I'm going to give you one of the proposals that purportedly resolves the paradox, which is the baby universe proposal. And I'm going to explain why time is really crucial to eliminating what seems to be the problem. But then we have to deal with something else. We need a way to coordinate time across the parent and baby universes. And while this may look like gibberish right now, I'm going to explain what transcendent entanglement means and what exactly is this auxiliary pairing structure that glues together and synchronizes what's happening in the original space-time that we start out with, and then the space-time that forms through black holes. And my question, I think I can give a pretty convincing argument, is that it seems like we would need some sort of objective global foliation if we're going to entertain this proposal. And the conclusion is that baby universes need parental watch. So let's get started with an introduction to the paradox. Black holes, I hope everyone knows what they are, at least on an intuitive level. They're regions of no escape. Not even light rays can get out for all future times. But something really interesting happens when you add quantum theory. So I want to rediscover Hawking's 1975 derivation, and there were a couple of ingredients that he used. First is just the classical geometry of a vacuum black hole solution. So if you imagine, we want to be able to describe how space-time and matter interact. On one side of the equation, of the Einstein field equation, you have, let's say, a Schwarzschild black hole, which is the simplest kind. It's just a stationary region, and there's an event horizon, that's the boundary. But there's no matter in this universe, so that's why it's a vacuum solution. But then on the other side, we want to describe that vacuum in a quantum way. So we're going to use quantum matter fields. And one of the simplest fields you can use is what's called a massless scalar field. And it starts out in a vacuum state according to the definition that there are no particles. So we just have a black hole space-time, we have quantum matter fields, but no particles. And this may sound pretty boring. I mean, what can really happen in such a model? It turns out it's not quite as boring as it seems, because we can still find some dynamism going on when we break apart the fields into waves with positive and negative frequencies that cancel out. And you can heuristically think of this as virtual particles of positive and negative energy. And there's this visual of these particles that are popping in and out of existence, and they basically borrow energy from the vacuum and settle the energy debt. And while that's a very poetic picture, let's just keep the dance part out of it. Let's just imagine that these particles are there, and they're there in just the right numbers so that they effectively cancel each other out. I just started watching Star Trek, and so to give you a better picture of what these Hawking pairs are like, I thought the alien species of binars is a good analogy, where these Hawking pairs are born to be bonded, just like these binars are genetically bonded to another for life. So these positive and negative energy particles, they come as a package deal. And why do they come as a package deal? Because of the quantum phenomenon of entanglement. So what that means is there are these non-local correlations where if you give me one of them, there's going to be vital information about the subsystem that I have that's not going to be contained in and of itself. Right? There's going to be vital information that's contained outside of it. And just to be a little more precise, entanglement is a mathematical property of quantum states, but I think it is very useful and very reasonable to interpret it as a physical relation between quantum subsystems. And as I intimated before, one thing that makes entanglement quite special is that information in the whole can't be reconstructed by the sum of its parts. So an entangled state, is a unit in and of itself. And while normally we have, these Hawking pairs that, they exist together all the time, and we get the vacuum by noting that their presence counterbalances each other. Black holes disrupt this balance because the event horizon is a causal barrier that can separate the Hawking pairs, where you get half of them, notably the negative energy partners, that get trapped inside. And then you have the other half that do escape really, really far away. And these are the positive energy partners. So the result we get, whereas, at one time we had the exact ratios to, recover the vacuum, at some point we're no longer going to end up with a vacuum state. When we look really far away, we're actually going to detect the presence of real particles with an energy spectrum depending only on the temperature that is related to the black hole's mass. And this looks like black body radiation, the kind of radiation that we're familiar with in everyday circumstances. And so here's a picture of what's going on. So the blue and green balls, you can think of the green ones as the negative energy partners, the blue ones as the positive energy ones. The negative energy partners get trapped in the black hole, and their destiny is to meet the ill-fated singularity, which annihilates them. And those that are left make it really far out, but because they're positive energy, now you're going to have something there that wasn't present before. And the links you see, that is symbolizing the entanglement between them. So Penrose diagrams are a really, really useful tool. And don't worry if you don't understand everything that's going on, but I'm just going to try to give you a sense of why this is a very useful depiction. So a Penrose diagram lets you preserve light cone structure, which means no matter the curvature in the space-time, you can always represent the trajectories of light rays or anything that's massless and would travel at the speed of light through 45-degree angles. So what's being shown here is we have time, that's the vertical axis where we're going from past to future. We have the radial coordinate. So at r equals 0, it's the origin of our coordinate system. You can think of it as the center of a black hole, although that's a little complicated. And then as you go out, you're moving farther and farther out in space. And this is the black hole singularity. This is the event horizon. This point E is a very interesting, ambiguous part of the diagram, but we're going to take it as a space-time event which marks the disappearance of the event horizon. So this is the final evaporation event. And what's really unique is that after the black hole disappears, we still have some space-time left, right? So we have this topological discontinuity. And now what we want to ask is, what is the global structure of an evaporation space-time? So let's look at our particles, and let's look at these simultaneity slices. And what we want to know is the space-time globally hyperbolic? So on each simultaneity slice, are you going to register all of the particles that should exist in this toy model? So here on sigma 1, that's pretty early on, before even the black hole forms, we can see we have 2 positive energy and 2 negative energy particles. The negative ones are blue that end up in the black hole, and the positive ones are red. So there we have a vacuum state, all good. On the next slice, sigma 2, we also have a vacuum state because we have 2 positive energy, 2 negative energy particles. But by this time, the negative energy particles are already in the black hole. The positive energy particles are outside, so this is during the evaporation period, because the negative energy particles are reducing the mass and size of the black hole. But then at late times, after the black hole has evaporated, sigma 3, it seems like we only have the positive energy partners left. So that's not a vacuum state, and half of what we started with does not make it to late times. And many people, although not all, have considered this a problem, but no one has articulated what exactly about this disturbs our intuitions. They have used information theoretic language to describe this, and while it might capture something, it doesn't capture everything. So the positive energy partners, that's what makes up the Hawking radiation, obeys the no-hair theorem, and carries no information about whatever it was that formed the black hole beyond the details that the event horizon would anyways give us. And the most that is includes the mass, the angular momentum or the spin, and the charge. And so, while it's the no-hair theorem, it really should be the three-hair theorem, but it's still not a lot of information. And then we've also lost information about the Hawking radiation itself due to the persistence of non-local correlations, because it seems like that bond, that genetic bond that they, that their existence depended on is still there somehow. But there's no other subsystem in the space-time by the time the black hole disappears where we can potentially recover the entangled state. So there are 2 problems that I've identified. One is what I call the diachronic problem. So late times, like sigma 3, contains the leftover Hawking radiation, only positive energy pairs. And that's because the negative energy partners no longer exist. They have been annihilated by the black hole singularity. And what the singularity does is it basically, puts an end to your world line. It puts an end to your existence in space-time. And you might think this is a serious threat if you commit to the metaphysical principle of preservation of being. What that means is, whatever the fundamental ontology, you think that maybe that should, be stable, right? You shouldn't be able to change the amount of the stuff that underlies the material world. And so there's this quote by Kant that reflects this sentiment, and it's actually quite prevalent throughout the history of Western philosophy, that in all change of appearances, substance persists, and its quantum is neither increased nor diminished in nature. So this is one problem that you might have with black hole evaporation. The second problem you might have is what I call the synchronic problem, where the mathematical form of the state of Hawking radiation suggests that the positive energy partners are still entangled. But with what? And in order to parse what's going on, I just want to remind you that entanglement, as I mentioned earlier, is a mathematical property of states. But the concept of a state usually relies on a notion of simultaneity. It's the snapshot of a system, as if it's frozen, and that snapshot lets you figure out what the parts are and how they're related to each other. And so here, what we would want to do is figure out, where in that snapshot is this other system that's entangled with Hawking radiation, but there is no other entangled subsystem that's simultaneous with that simultaneity slice, and it seems like it's nowhere to be found. Because no matter how we carve up the space-time, we might have thought a very natural inclination is to say, oh, it's still entangled with the negative energy partner, but that only belongs to the past. The simultaneity slices are to the past of the final evaporation event. So we have what I call a paradox of phantom entanglement, where Hawking radiation seems to simultaneously be a global system, that's all that's left in the universe, as well as an entangled subsystem. It's as if it's entangled with the phantoms of the partners with which it was previously entangled, but it hasn't gotten the memo, right? One of the binars is still communicating with the ghosts of its pair. And this is a really, really bizarre situation. I mean, how can it be that something that's doing physical work, like a ghost, is intangible, immaterial, and yet bears on our concrete phenomena? So I think this is truly a metaphysical absurdity that needs to be corrected. And how can you do so? Well, you can either say that Hawking radiation is just a global system, and then you need to give me some story about how the entanglement breaks and why it breaks or what happens. And that's one that's actually has not really been explored in the literature. Hawking tried to go in that direction for a little while, but it just has not sustained momentum. The most common response in the literature is to physicalize what we thought was phantom and say, no, Hawking radiation really is an entangled subsystem. Now, something needs to give, some changes need to be made, but we need to find that entangled system somewhere in the space-time such that you can take a snapshot of the universe and you can say, okay, there's Hawking radiation as a subsystem in one place and this entangled subsystem somewhere else. And the reason I think this really is a problem that hasn't been appreciated is because you see sentiments that something is terribly wrong, but it hasn't been articulated quite this way. So one of the foremost opponents of information loss says all hell would break loose in all of physics, not just black hole physics, once the door to information loss was opened. And I agree with that if you buy into what I'm trying to convey, that there really is a threat to physics being described by concrete entities in the ontology. But funnily enough, not everyone has quite gotten on board with the bite of phantom entanglement. And there's this quote that I really love about how there's actually a sociological explanation for this. The controversy can be cast as a clash of subcultures in physics, with the high-energy physicists typically eager, if not desperate, to avoid the paradox, while the general relativists are generally more prepared to embrace it. So why is that? I think if you put your relativist cap on, you're probably just focusing on the diachronic problem. Okay, so what? if we find out from our best physical theories that the fundamental ontology, the amount of it can vary over time. That's something that physics should tell us, not something that we should have an a priori commitment to. And even before black holes evaporated, we still had singularities. We still had these very exotic space-times where that Mark was talking about with closed time-like curves, and it seemed like you couldn't even track through some sort of global time function what was going on with the material world. So if you can't track it, it seems kind of moot to insist on it. So this is 25 minutes until, for the entire thing?
No, you started 25 minutes ago.
Oh, I started 25 minutes ago, so I have 35 minutes left.
Yeah.
Okay, okay. That includes Q&A.
Okay.
Yes, okay. Yeah, so you might be like, the diachronic problem is not such a big deal. But the synchronic problem is a big deal, and it includes within it the diachronic problem. Because the reason we have these phantom entities that are still entangled with Hawking radiation is because they disappeared due to the singularity and the non-globally hyperbolic structure of the space-time. And the only way to get rid of the synchronic problem is to also get rid of the diachronic problem. So how are you going to do that? Paradox resolution calls for global quantum states describing entanglement relations, but in relativistic contexts, a simultaneity slice mandates space-like separation among subsystems. And when you look at relativistic geometric structure, that means you need a hypersurface that sort of, is orthogonal to your light cone. And as I said before, if we take a snapshot by Hawking radiation somewhere here, it means I need to find the entangled system, somewhere there on that hypersurface. And so our goal is to locate another subsystem entangled with Hawking radiation. And I'm going to skip over this part because of time. So it seems like one thing we could do, which Erman briefly mentions, is to plug the information leak by eliminating the singularity. I do think it's necessary, and that's based on an example I didn't go through, but other physicists agree that that seems to be one of the most straightforward ways to actually create more time. So the problem, it could be that the black hole from the inside has plenty of space to store whatever subsystem you need that would be entangled with the Hawking radiation. But the singularity cuts their time short, right? That's the meaning of, puts an end to the world lines, to their trajectories. We need more time to either turn the black hole into a safe house, to evacuate whatever is in the black hole and get it out, or both. And the baby universe takes this first option. We're going to turn the black hole into a safe house. So how does this work? Space-time is extended beyond the singularity into a bounded region. Anything that enters a black hole exists indefinitely according to the proper time of the object that is lucky enough or unlucky enough to do so. And the black hole, after the final evaporation event or at the final evaporation event, pinches off into a baby universe. So even though the event horizon disappears in the parent universe, there is this closed region of space-time that has been born because of the process. And how do you solve the problem? Now that you have more time, you can actually find simultaneity slices that can be paired with the one we were trying to pair it with before. And this, of course, belongs to the domain of quantum gravity because eliminating singularities is one of the guiding principles for any theory of quantum gravity that would like to achieve a lot of the things that we can't achieve in our current theories. So just to give you a visual, this was the slice we were looking at before, which had the Hawking radiation. And now by eliminating the singularity and extending, creating more time, we now have a simultaneity slice over there, sigma baby, and that could contain the subsystem that's entangled with the Hawking radiation. But it means we need to add structure to do this. And why is that? The parent and baby universes are not connected directly via the metric. There's no space-like separation between them. But they must be connected directly in some sense, because the reason they're solving the problem is that they sustain these entanglement relations that transcend the disconnected space-time regions. So that's why Baptiste and we came up with this phrase. We call that transcendent entanglement. And what are the implications? So we need some sort of pairing relation that lets us consider it a unified state. And this relation must uniquely associate simultaneous slices across the parent and baby universes. However, keep in mind that this pairing relation is not defined as simultaneous from the space-time metric. So we have, let's say, one Hawking partner there and the other one there. The red depicts the entanglement relation. They are on the simultaneity slices, but to be deemed simultaneous with each other, we need something mysterious to connect them. So it signals the existence of unknown auxiliary pairing structure. Right now, there's no presupposition about what's more fundamental. Is the entanglement relation more fundamental? Is this new notion of simultaneity more fundamental? Or can they even be collapsed into one and the same thing? But we have some candidates for what it could be. It has to be either some sort of non-spatiotemporal structure, perhaps coming from a theory of quantum gravity, or it could be a second-order metric that gives us meta time. So the question is, does this auxiliary pairing structure give us an objective global foliation? So if we imagine space-time as a loaf of raisin bread, is there only one way the mighty knife of time can slice this thing up? And Maudlin acknowledges there may be a problem for retrodiction from the relativistic side. It is not evident how to determine how these two pieces across universes fit together. And the reason we're worried about relativity is because transcendent entanglement does violate Lorentz invariance. You can't transform from one foliation to another. And so the main question I want to ask is whether this implies an objective global foliation. A weak notion of this auxiliary pairing structure might say no. I think the more convincing answer is yes, in which you have a stronger pairing relation between the two universes. But let's see what they each have to say. So I'm going to skip this. So in weak APS, you're going to be selecting foliation-dependent relations, but theoretically you can still have infinitely many foliations. So previously we looked at the blue foliation, but boosted relative to that, in which the slices in each universe undergo some transformations, and so now you have this new foliation. There are new pairing relations that are shown in the white segments. But in any other foliation, you're not going to have entanglement, or at least in the same way. Which means that entanglement that was simultaneous in one foliation is now going to be across time in the other foliation, and therefore the previous pairing relations would also not carry over once you go to another coordinate system. And that's why in weak APS, the entanglement itself can't give you that auxiliary pairing structure. It must be something else. And I think that's why it has to be non-spatiotemporal to avoid interfering with transformations that do act on space-time. And you might think this is appealing because it's in the spirit of a non-spatiotemporal theory of quantum gravity. And the idea is that you have to recover space-time from this non-spatiotemporal ontology, and you would do so at the effective level. And you would also recover relativity at the effective level. Something sounds really fishy to me about this way to go. I think it lacks consistency. I mean, how can each space-time individually be relativistic, but the space-time globally is not? I can't really make sense of this. I have the feeling that there might be the seeds of contradiction somewhere. And it's important to note that approximately won't cut it, because approximately means that only one foliation would be physically admissible. And I don't think quantum gravity would provide a helpful narrative on emergence, because you would need a disjointed theory. You have your fundamental ontology, you have space-time emergence, but then you need something else to connect, what emerges that can't have a story about space-time emergence in and of itself. So you need a mixture of ontologies, laws, and symmetries, and it seems very messy. It goes against the scientific ideal of unification. So I think the more reasonable interpretation of what's going on is that a strong relation between any two such simultaneity slices will pick out an objective global foliation. So you're going to have a second order metric. There's going to be this master clock or meta time that defines simultaneity across universes. And this is where the slogan comes from, that baby universes need parental watch. They're constantly under the guidance and synchronization of the parent universe that gave birth to them. And then there's an interesting question to be had. Does transcendental entanglement exploit this second order metric, or does it ground it? And I think that's going to depend on the quantum gravity approach, but as of right now, there's no serious contender for that happening. So, I think we really just need to bite the bullet and accept some sort of meta time, in the spirit of what Sam was talking about earlier. But this also may not be very attractive because it is definitely ad hoc. You're just adding a metaphysical time to make a proposal favorable when it's certainly not the end of the word. And it definitely undermines the prospect of a non-spatiotemporal ontology in quantum gravity. So either it casts suspicion on this whole proposal from the get-go, or motivates a spatiotemporal theory of quantum gravity where at least time is fundamental. You might even have a different story about space, but time has to be there from the beginning. And through the grapevine, there are some people who are in favor of this way of thinking. So several proponents of the baby universe proposal are independently committed to an A theory of time. That includes Lee Smolin, who in his book Time Reborn defends both baby universes and an objective global foliation. And then Maudlin is an outspoken Bohmian, and he defends a variation of the baby universe proposal in his reaction to the information loss paradox. So I hope to have, I know this was a very technical topic, but I hope I was able to distill it to the physically intuitive picture and convinced you that strong auxiliary pairing structure seems more reasonable than weak auxiliary pairing structure to make sense of transcendent entanglement, which is what we need to solve the problem of phantom entanglement, make sure there's a physical system that's entangled with Hawking radiation, but also make sure that they're coordinated across disconnected spacetimes or separate universes. And if this proposal is correct, then I think space-time is objectively foliated. Baby universes need parental watch. Is that problematic? Probably. If the child is like any other child, it's very much problematic to constantly be under surveillance of your parents. But you tell me whether you think this is an intriguing proposal or you think it should be set aside for something else. Because it depends on what you gauge to be a more promising research program for quantum gravity. Whether we want to explore non-spatiotemporal ontologies or we really want to hold on to an A-theory-based ontology. So thank you very much for listening.
Thank you, actually, it was very impressive. Questions? Sam?
Let someone else go first. We'll be done. This.
Mark?
Well, more remarks than questions. I don't know. I don't see where you need quantum gravity because you can have prolongation. I mean, a topological prolongation of space-time through the singularity without invoking quantum gravity, because quantum gravity gravity is the metric of space-time, not the topology of space-time. And here you're changing the topology, which is not really quantum gravity. This is just like in many black hole solutions, or in anti-de universe, or in many cases, you can change the topology of space-time without changing really the metric. So this is a question. But I have another question also. So you want to associate information with entanglement, which is a good idea in quantum field theory. But what I don't understand is why you require a foliation. Because, for instance, when you have entanglement in usual quantum field theory in Minkowski spacetime, it is true that when you express entanglement, you use coordinates and you choose a foliation. But you don't need that because the fact that Minkowski spacetime is Lorentz invariant means that you can choose any foliation. So you can consider that your right particle is entangled with the right particle here or there at another moment, and this will change nothing. So I think you don't need to look at foliation. I'm not sure I'm correct, but this is also an open question. I think you can define entanglement in a Lorentz covariant way, which means that you don't need a foliation to express entanglement. This is not what is usually done, but I think in your case this is correct. So you don't need to introduce this foliation between disconnected part of space-time, and you don't need to introduce your meta time. That I don't really understand. And the last point is that if you are ready to invoke quantum gravity, this means that the gravitational field, or if you prefer the metric of space-time, because this is more or less the same thing, can be entangled with matter, because this is a field like the magnetic field or like in a matter field. So when the particle inside the black hole disappears, this doesn't mean that entanglement disappears, because your external particle can become entangled with the gravitational field itself. And this is the usual solution to the information paradox, because the horizon, of course, in general relativity, horizon has no degrees of freedom, but in quantum gravity, horizon has a lot of degrees of freedom, and this number of degrees of freedom is the origin of the entropy of the black hole. But this means that the degrees of freedom of the horizon, which are purely gravitational, purely geometric, can be entangled with the external particles. So you don't need to invoke internal particles, which have disappeared, to speak about entanglement of your external particle with something, and this something is just the metric properties, the quantum metric properties of the horizon.
Okay, so I have a response for all of your comments. Let me just quickly go to the Penrose diagram.
Just adding just one sentence, I think that in some sense, when you say that the external particles are still entangled with internal particles in your addition to spacetime, this could be equivalent in some sense to say that they are entangled with the horizon quantum characteristics. I think this is more or less the same thing, because from outside you cannot check if you have an internal part of spacetime or not. You will see only the horizon.
Okay, so actually let me address that last point first. In Hawking's derivation, the matter fields are not coupled with the metric. So the matter fields are basically traversing geodesics, and in that case, you would not have the matter fields being entangled with the metric fields. So the original paradox that arises cannot make use of that solution. And I do think that's actually a pretty formidable assumption that needs to be added to make sense of black hole evaporation. It's, I think, quite remarkable that the matter fields somehow know about what the gravitational field is doing, even though they're not coupled. And to give you the story about black hole evaporation, you have to put in the assumption that they're coupled and certain energy conditions hold by hand to say that the energy that comes out with radiation exactly compensates for, you know, the mass that's lost in the black hole. So to say that you know, the quantum matter fields are entangled with the metric fields, you would still need to give me a story about how the entanglement is transferred from one to the other. Or you would say that actually the underlying degrees of freedom are unified. You know, there's, you know, you kind of zoom in long enough and there really is no substantive difference between the matter degrees of freedom and the metrical degrees of freedom. And then I think we're already foraying into quantum gravitational territory.
This point is generated for quantum gravity theories because...
So that's why you would need a quantum gravity theory.
Yes, but in your solution, you invoke quantum gravity. So this means that the gravitational field is quantic, and so here in the black hole, matter interacts with gravitation, and this interaction creates entanglement. Exactly like matter particle, when they interact with photons, they are entangled with electromagnetic fields. It's exactly the same situation. And this is in some sense the definition of quantum gravity. This means that the gravitational field is quantum, so when you interact with it, you are entangled with it. It's like for electromagnetism.
And so you're basically just expressing your preference for another proposal. I said that I'm focusing on this proposal not because I'm an advocate for it, because it has something interesting to say about time and might give us a reason to disregard it. What you're saying is in line with Alejandro Perez's proposal from Marseille, which is basically a hidden variables explanation, that you have these hidden gravitational degrees of freedom that are just not being accounted for in the semi-classical description. So yes, I mean, you can, of course, there are tons of proposals out there. I picked this one to have something interesting to say about time because I think it really is trying to revert back to a pre-relativistic understanding of time. And then your other question about why we need a foliation. So of course, in technical language, the main worry for the particle physicists was unitarity. And it seems like global hyperbolicity is a necessary condition for unitarity, and that's why having the space-time foliable into Cauchy surfaces enters the dialectic. But as far as entanglement goes, I agree. I mean, in quantum field theory on Minkowski space-time, entanglement is covariant, but what it means is you can have entanglement across time, and that does not solve the synchronic problem, because if we need the space-time to be foldable by Cauchy surfaces, it doesn't matter if you can transform such that entanglement is across time or synchronous. We need to be able to extend sigma 3 into a proper Cauchy surface.
Thanks. I think we should, for what's in the
Absolutely.
expertise, Dan.
Thanks. Thank you. Yeah, really interesting. Can I just a clarificatory question?
Yeah.
Can you just give me the case against the weak APS again?
Absolutely. So I know I just plowed through that. Okay, so imagine for weak APS, you have this parent structure. It can't be spatiotemporal, otherwise that would just completely interfere with us being able to, relativistically transform, the slices in each universe. And if we're going to go with non-spatiotemporal structure to begin with, we might think the entire fundamental ontology is non-spatiotemporal. So you have, I'm using degrees of freedom to kind of be synonymous with whatever these fundamental entities are. I know it's not an exact synonym, but just, grant me on the language. So let's say you have your non-spatiotemporal degrees of freedom. What it means is that a subset of those degrees of freedom are giving rise to space-time in one universe. Another subset of those degrees of freedom are giving rise to space-time in another universe. You need some degrees of freedom that are left over that, it's not giving rise to anything metrical. But the leftover degrees of freedom are somehow connecting these two. And I don't think a standard story about emergence will do, because if you truly had a unified ontology at your base level, why wouldn't you just have space-time emergence for, for everything? Why would you have some degrees of freedom that are left over that are playing a radically different role? And that was my intuition why that you would really need a disjointed theory where you have two different fundamental ontologies, one of which gives rise to space-time that recovers relativity, another which gives rise to something else, but is also somehow interacting with the emergent ontology. I mean, then it becomes, quite hard to keep track of. So that's my sense that I think there must be a contradiction somewhere to say that, yeah, the parts are Lorentz invariant, but the whole is not.
Thank you. That's really clear. Thank you.
Yeah, so my question is kind of similar.
Yeah.
I mean, I'm not sure whether this is weak. I forgot the terminology. So what's the choice? You've got weak when you dismiss. You've got the links and then the...
Yeah, let me go there. Okay.
Cool. Right. So, I mean, if I've got two disjoint spacetimes,
yeah,
but with spatial boundaries, so they could be Lorentzian, they could have a Lorentzian metric. So in that sense, they're invariant.
Yeah.
It seems to me I can make sense of a quantum theory that assigns a pure state, which is associated with a foliation, one slice of a foliation in one slice of a foliation in the other, that involves entanglement between the two. But just as in standard case, given that state, I can consider different slicings and different states, and the state on a sub part of the slice is not a well-defined thing, it's only defined relative to the entire slice. Seems I can say all of that for this setup. So I've got foliation invariance, and yet there is the pure state only exists over the two. And I think in that case you've got a kind of link, because there will be a kind of identification on the boundary. So you've got, I can consider any kind of foliation of the disjoint spacetime I like, except that foliations, well, not any foliation of the disjoint, there's a kind of, this boundary point, an allowed foliation here will always be matching a boundary point here to a boundary point here. And of course, in this case, that's not the topologies of the space-time you end up with when you have black hole evaporation. But I'm just not seeing, you know, a priori why something like that isn't possible. Why I can have entanglement, but also foliation between the two, but also that degree of foliation variance.
So what you're saying to me sounds like this procedure. Oh, sorry. Where you have the two foliations, you know, the set of partial Cauchy surfaces in the baby and parent universes, and then you have some set of relations. In your case, you said, you know, basically like matching boundary conditions that unite the two, and then you could represent the whole thing as a pure state. Mm-hmm. But to transform it, I feel like you would have to apply the Lorentz transformations to each foliation separately.
So not, I mean, it's kind of, they're not really Lorentz transformations. I'm considering arbitrary refoliations, which are, I mean, it's like the, so I can, I mean, in this case, if I'm considering a given foliation, a given slice here, there will be lots of foliations here, such that I can consider a pure state on those, on those slices, and what the mixed state of this slice will be dependent on what slice I'm choosing here. But that's all fine. But I can't, for example, combine that slice with that slice or something. So I've got to. There's some restriction.
Right.
I've got to. If I'm fixing what I'm looking at over here, I fix the boundary conditions in this case. So yes, it's not all possible unions F, A, F, infinity that are allowed.
Oh, of course, it would be a unique.
Right.
It would be a unique association.
Yeah.
But then, you know, when you go from one foliation to another, you would need a new set of relations that tell you what the association is. And I mean, maybe that's something that you can tell me more about afterwards. I'm not aware of how you would have. I don't know how you could just act on the entire pure state if your goal is you want the you know, disjointed parts of the state. When I say disjointed, I mean metrically, but you know, you basically divide the state and you want certain parts of the state to transform Lorentz invariantly. I don't know how you would transform the entire pure state to get that. I feel like you would have to do it in multiple steps by breaking up the states into the relevant subsystems, and that led to my worry over having a disjointed theory where you really have different sets of laws operating on different parts of the state. Now, if you want some sort of transformation that's not Lorentz invariant, go for it. But the concern here was Lorentz invariance in particular.
Yeah, so I guess certain kinds of transformations, certain kinds of freedom would make sense. But it's a big jump from that to saying, so I'm not going to have any transformation. I've got one preferred true foliation. So that's, you know, there seems to be a jump.
So if you have some transformations, but they don't give you a preferred foliation, what would be the in-between? Well, like where the transformations aren't the Lorentz transformations, it's something else, but you still don't get a preferred foliation as far as time ordering goes. What would be the compromise?
Well, I mean, so I'm just not clear on the details. So if I've got I mean, in general, I'm not going to be able to get from the state on one slice to the state on another.
But what I'm asking is, are these transformations, I mean, of course you can have arbitrary transformations, but would the laws of physics be the same in
Yeah, I'm not saying there's, actually I think that you will be able to, I'm not seeing the problem. I'm just not seeing the problem. So there's if you want to know what the pure state is of the, combined system, then there's only certain variations that are allowed. But it seems to me the physics within it, each part will, you've got mixed states defined on the variations, and you can consider any variation you like. I'm not saying there's a problem with the local physics.
I do think you can consider any foliation you like, but I think there's a symmetry breaking where the laws of physics won't be the same across foliation. So if you think the laws of physics, that's the true set of laws in one of the foliations, then I think that would be your preferred foliation.
Yeah, I don't think so, but we need to talk about it.
Sure.
Yeah, thank you very much.